We're now going to turn to the derivation of uncoupled equations, decoupled equations for the electromagnetic potentials. So let's start by reminding ourselves that B is equal to the curl of A, and that E is equal to minus the gradient of V, the scalar potential, minus dA by dt. And A, of course, is the vector potential. And we're going to substitute these into the Ampere-Maxwell equations. We're going to, the Maxwell equations. We're going to use the Ampere-Maxwell and Gauss equations, or Gauss's law, an Ampere-Maxwell equation, if you like, in order to derive some equations for A and for phi. And then we're going to use the Lorenz condition, which we discussed in the previous video on gauges, in order to decouple the equations. So Ampere-Maxwell says that curl of B is equal to mu naught J plus epsilon naught mu naught dE by dt. And so what we're going to do is we're going to substitute in for A and for V. We're going to derive an equation which is complicated. We saw that in the last video. We'll do the same for Gauss's law and get an equation for V. And then by applying Lorenz, we'll be able to decouple these. Once they're decoupled, then we can solve them. So if we substitute in, then we have the curl of A is equal to mu naught J. So J here is the source term, so we're always going to keep that, plus epsilon naught mu naught into minus, sorry, I forgot a d by dt. D by dt of minus grad V minus dA by dt. When we expand out curl of curl, we get the following. We get the gradient of the divergence, grad of div A minus del squared A. We get an epsilon naught mu naught grad of dV by dt. I've taken that across from the right-hand side. We get an epsilon naught mu naught d2a by dt squared, and that's equal to mu naught J. So if we just take terms, so this term on the right-hand side becomes this term on the left, and the minus sign here is cancelled when we take it. Similarly, this term becomes this. Now I'm going to multiply through it by minus 1, so that I've got a del squared, which is positive, just because that's easier. So we have del squared A minus epsilon naught mu naught d2a by dt squared. That's the wave equation part that we might be interested in. We're going to have minus grad of div of A minus grad of epsilon naught mu naught dV by dt. And if you remember back to the Lorenz condition, you can see why I've written it like that. And that's going to equal minus mu naught J. So that's the key equation for A. That's the equation that we get when we start simply from the Ampere-Maxwell equation. It's a complicated equation. It involves both A and V. It involves first and second derivatives, and it's a mess, frankly. If we now go to Gauss's law, we have that the divergence of E is equal to rho over epsilon naught, and that tells us that when we substitute in that the gradient of the divergence of minus grad V minus dA by dt is equal to rho over epsilon naught, and therefore del squared V minus d by dt of div A is equal to minus rho over epsilon naught. Again, it's a mixed equation. It includes no time variation of V, and we want to get rid of it. So, coming back to the equation for A, which I'm going to label as equation 1 as opposed to equation 2 for V, we see that inside the gradient we have two terms, div A and epsilon naught mu naught dV by dt. So we recall the Lorenz gauge, where we set div A plus epsilon naught mu naught dV by dt is equal to 0. And therefore, if we rewrite equation 1, we get the following. We have del squared A minus epsilon naught mu naught d2a by dt squared minus the gradient of div A plus epsilon naught mu naught dA by dt is equal to minus mu naught J. And as I said at the end of the last video, this term here becomes 0 in the Lorenz gauge, and so we get an equation for A, which is simply del squared A minus epsilon naught mu naught d2A by dt squared is equal to minus mu naught J. And we'll give that number 3. Now, how do we use the Lorenz gauge for the potential? So in the Lorenz gauge, we have that the divergence of A is equal to minus epsilon naught mu naught dV by dt. And I'm just wanting to check that I haven't lost a minus sign. I have lost a minus sign. This should have been a plus up here. When I multiplied through by minus 1, I'm sorry about that. I realised that as I was writing it out. So now let's substitute this into 2. Now that I've corrected equation 2, and we find the following, we have that del squared V plus d by dt of minus epsilon naught mu naught dV by dt is equal to minus rho over epsilon naught, and therefore del squared V minus epsilon naught mu naught d2V by dt squared is equal to minus rho over epsilon naught. And that is equation 4. Let's just highlight equations 3 and 4. There's equation 3. And here is equation 4. Those two equations pay back some study. Notice that we've got exactly the same form. We've got on the left hand side we have the wave equation on either the vector or the scalar potential. On the right hand side we have the source term. So the source of the vector potential in the Lorenz gauge is purely the current density. The source of the scalar potential in the Lorenz gauge is purely the charge density. When we want to solve these, it's actually now much easier than it was before, because we're simply solving for the wave equation. So if we were to set the sources to 0, then that would just be the standard wave equation. We know how to solve that. So we can use all the techniques that we've learned for partial differential equations to solve for the specific solution where we set the charge densities on the right-hand side. Notice that we can actually break down the equation for A into 3 separate components, for instance x, y and z, and solve each of those individually. So Ax can be solved with Jx, the source, Ay and Az. So the next thing that we're going to need to do is to solve those equations, and that will be the topic of the next video. There are going to be 2 ways that I approach this. I'll probably split it into 2 videos. In the first video, what we're going to do is we're just going to simply quote the solution. We're not going to try and justify it. We're not going to say where it comes from. We'll just say what the solution is, and then we'll check that that actually satisfies the equations. This is one way of doing things in physics, though it's perhaps less satisfying. And then in another video, I'll give you an introduction to how we can actually go about solving these things. So that completes the sort of the introduction to the way that we use the scalar and vector potentials. There are 3 videos. The first one on motivating why we use the potentials rather than the fields. The second one talking about gauge freedom. And then this third one talking about how we create these equations for the potential.